Hi, my name is Michael Pendazis, and this is Math 231, Linear Algebra, online lesson number 3. Last lesson, we finished 3.3, and we covered 3.4, the geometry of linear systems. This class, we will talk about 3.5, cross product, 4.1, real vector spaces, and if there's time, we will talk about 4.2, subspaces. So let's start with 3.5. Okay, so for 3.5, definition 1, if U and V are in 3 space, vectors in 3 space, then the cross product U cross V is the vector defined by U cross V is equal to U2 V3 minus U3 V2, comma, U3 V1 minus U1 V3, comma, U1 V2 minus U2 V1. Or, in determinant notation, U cross V is equal to the determinant of U2, U3, V2, V3, comma, negative U1, U3, V1, V3, comma, U1, U2, V1, V2. This is equation 1 in this section, 3.5. Okay, and so this is the definition of the cross product of 2 vectors in 3 space. Okay, so this is definition 1 at 3.5, and it defines the cross product U cross V of 2 vectors in 3 space. Okay, so it's important to note that these 2 vectors U and V are 3 tuples. They're vectors in 3 space. They're vectors with 3 components. Okay, and so you find the cross product U cross V, you find this by finding that. So you can write it this way, but it's harder to visualize what U cross V is looking at this equation. It's much easier to visualize what U cross V is by using that equation. Okay? And actually what this expression is, it's just, this is equal to the determinant of I, J, K, U1, U2, U3, V1, V2, V3. And so actually memorizing this entire complicated formula can just come down to finding the determinant of that matrix. Okay? So if you find the determinant of this matrix, it equals that. Okay? So U cross V, you can say the shortest way, the easiest way to remember this is U cross V is equal to the determinant of that matrix. And you'll get that 3 tuple. Okay, so make sure to write this down. U cross V is equal to the determinant of that matrix. Okay. Okay, so example 1, 3.5, is the following. Find U cross V, where U is equal to the vector 1, 2, negative 2, and the vector V is equal to the vector 3, 0, 1. Okay, so the solution is u cross v by definition is equal to the vector, the determinant of u2, u3, v2, v3, comma, negative determinant of u1, u3, v1, v3, comma, determinant of u1, u2, v1, v2. And so I'm remembering this because I'm thinking of the determinant of the matrix from the previous page. The previous page it said u cross v is equal to the determinant of I, j, k, u1, u2, u3, v1, v2, v3. Once you get good at calculating determinants, you can visualize that the determinant of this matrix has these components. Okay, so it's about knowing how to calculate the determinant of the matrix, having practiced calculating determinants. And once you calculate enough determinants of matrices, easy ones, you'll start to be able to see what the determinant of a matrix is. And so once you practice this a bit, you can see that the determinant of this matrix is that 3 tuple. Okay, and so u cross v is by definition that, which I told you is also this. Okay, so now we're just going to calculate this. So remember, this is u1, this is u2, this is u3. This is v1, that's v2, and that's v3. And so you're just going to calculate those 6 values into that expression. And so calculating, just plugging in, we get that this is 2, negative 2, 0, 1. Negative the determinant of 1, negative 2, 3, 1. Comma determinant of 1, 2, 3, 0. Okay. And so now we have the determinants are the components of this vector, and then determinants of this matrix, right? You just do that to find the determinant. 2 times 1 minus negative 2 times 0, and you get 2 here. The next component is the negative of this times this minus that times that, and so it's 1 minus negative 6, which is 7. Negative that is negative 7. Comma, the last one is 1 times 0 minus 2 times 3, that's 0 minus 6. That's negative 6. And so u cross v is equal to 2 comma negative 7 comma negative 6. Okay, and so in this example, we're applying the definition of a cross product of 2 vectors in 3 space, 2 vectors with 3 components, and we're calculating their cross product using the definition on the last board. Okay, so by definition, this is equal to that, and then we plug in the values of the variables into that formula, into that expression, and we calculate the determinants, and we get that. Okay, so that's example 1, and so that's showing you how to find the cross product, again, of 2 vectors in 3 space, or 2 vectors with 3 components. So next is the theorem. So this is theorem 3.5.1. So if u, v, and w are vectors in 3 space, so I'm abbreviating this by saying u, v, and w are vectors in 3 space, and k is a scalar, then actually, sorry, we don't need k as a scalar. Then u dot u cross v is equal to 0. B, v dot u cross v is equal to 0. C, the norm of u cross v squared is equal to the norm of u squared, norm of v squared, minus u dot v squared. D, u cross v cross w is equal to u dot w v minus u dot v w. And then E, u cross v cross w is equal to u dot w r, v, sorry, minus v dot w u. Okay, so theorem 3.5.1 gives you 5 more equations. Okay, so we now have these 5 equations given 3 vectors in 3 space. Okay, and so part A, what part A is telling you is that the vectors u and u cross v are orthogonal. Okay, so if you're saying u dot u cross v is equal to 0, 2 vectors are orthogonal or perpendicular when their dot product is 0. And so the vector u and the vector u cross v, so when you take the cross product of 2 vectors, you get another vector. So this is a vector. That's a vector. There are 2 vectors. When you dot product them, you get 0. That means that they're orthogonal or perpendicular. And so this equation is telling that u and u cross v are orthogonal. It's also telling you in B that v and u cross v are orthogonal. So we're seeing here that because the dot product of the vector v and the vector u cross v, their dot product is 0, you can say v and u cross v are also orthogonal or perpendicular. Okay, so when you have 2 vectors u and v, and say you have a vector u here and a vector v there. So if you just take 2 vectors and you find their cross product, you're going to get a third vector u cross v that's perpendicular to both u and v. Okay, so that's what A and B are saying. That if you take 2 vectors, u and v, and you take their cross product, the result is another vector that's orthogonal or perpendicular to both u and v that you use to make u cross v. Okay. Okay, and then C is just a relationship between the norm of u cross v and the value of this expression. And so C, D, and E are just showing you relationships with things that happen when you take cross products and dot products. Okay. This expression is equal to that, that's equal to that, this is equal to that. And so A and B just tell you something very specific about the geometry happening, and then C, D, and E are kind of just values that are the same. Okay? And so these have names, but you don't have to worry about them. Okay, and so, so you have these 5 equations, and you can look back at the video and you can look at these equations again. And if you want to write them down, and you can pause the video and copy them down. Okay. Okay, so at any point, if you feel like the lesson might be going a little fast or you want to write something down, you can always pause the video, write down what's on the board, unpause it, and then keep watching. Okay, so let's continue. Theorem 3.5.2. So in this theorem, if u, v, and w are vectors in 3 space, which I just say u, v, w, and R3 for short. So if those 3 are vectors in 3 space and k is a scalar, then we have the following 6 equations. A, u cross v is equal to the negative of v cross u. That's called anti-commutativity. B, u cross v plus w is equal to u cross v plus u cross w. Okay? And then C, u plus v cross w is equal to u cross w plus u cross plus v cross w. Okay, so A, B, and C are easy to visualize. D, k times u cross v is equal to ku cross v, which is equal to u cross kv. E, u cross 0 is equal to 0 cross u, which is equal to 0. And then F, u cross u is equal to 0. Okay, so in Theorem 3.5.2, we now have these 6 equations. Okay, and so again, when I just showed you 11 equations, even though it sounds daunting to have 11 equations presented to you, this is making your life easier. Okay, the more I tell you, the more you know, the more things you can use to get the answer to a problem, right? And so there's actually now 11 equations between these 2 theorems that tell you relationships about the cross product that you can use to get the answer to a problem. Okay, So u, v, and w are vectors in 3 space. They're vectors with 3 components. K is a scalar. We have these 6 equations. Okay. A, this is called anti-commutativity. What that means is that if you take u cross v, it does not equal v cross u necessarily, but it equals negative v cross u. Okay, so if you take the cross product of 2 vectors, if you switch the order of the vectors you're cross producting, you get the negative of what you had before. Okay, and so by switching the order of u and v, you're getting the opposite vector to what you had before. It has the same magnitude, but you're taking the opposite direction of that vector. Okay, that's what happens when you take the negative vector. You get a vector that's directed in the opposite direction, but of the same magnitude, same length. Okay, u cross v plus w is u cross v plus u cross w. So this looks a lot like what's called left distributivity in multiplication. Okay, this would be called right distributivity. U plus v cross w is equal to u cross w plus v cross w. So here in D, you're taking this constant k and you're multiplying u cross v. So what D is telling you is that instead of taking u cross v and then multiplying by k, you can multiply u by k and then take the cross product with v, or you can multiply v by k and then take u cross kv. You have to keep the order the same. U is on the left, v is on the right. But you can move the constant from outside the cross product to multiplying either one of the vectors, and it's the same. Okay. E is simple. What E is telling you is that any vector u in R3, any vector with 3 components, if you take the cross product with 0, you get 0. Okay, and that doesn't matter the order. So you could take u cross 0 or 0 cross u, and they're both equal to 0. Okay, and F, u cross u is equal to 0. That means if you take any vector u, any arbitrary vector u in 3 space, any vector with 3 components, and you take the cross product of it with itself, you get 0. Okay, and so these are all important facts about the cross product. Okay, if you want to write some of this down, you can pause the video and write it down. Okay. Okay, now if we're looking at 3 space, again, if we're looking at R3 again is the set of all 3 tuples where each component is a real number, right? If this was the x-axis, this was the y-axis, and that was the z-axis. I is the standard unit vector in the positive direction of the x-axis. There's j, and that's k, right? So I, j, and k there. I is the vector 1, 0, 0. J is the vector 0, 1, 0. K is the vector 0, 0, 1. And so that those are the I, j, and k are the standard unit vectors of R3, right? I, j, and k are the standard unit vectors of R3. You can think of them as kind of the building blocks of R3 because you can take any vector in 3 space and represent it uniquely as a linear combination of I, j, and k, whatever that means, okay? So I, j, and k are called, again, review for another class, are the standard unit vectors of R3, okay? And so this is an important note about these vectors I, j, and k, the standard unit vectors of R3. If you take I cross I, it's equal to 0, right? If you take j cross j, it's equal to 0. If you take k cross k, it's equal to 0, right? So if you take any of these standard unit vectors and you cross product with itself, you get 0. Okay, and so that was from the last equation in the last theorem. If you take the cross product of the vector with itself, it's 0, right? Now there's a figure in the book, and so this is figure, let me just draw a circle here. This is figure 3.5.2 in the book. Okay, and so in figure 3.5.2 in the book, they draw a circle, they draw I here, they draw J here, and they draw K there. And what this is it's a picture to help you memorize the cross products of standard unit vectors in R3. All it is the circle oriented clockwise, meaning you think of yourself as walking around the unit circle in a clockwise direction, the same direction as a clock hand moves on the clock, right? You have a clock, and this is, let's say, 12, this is 6, this is 3, this is 9. The time goes in this direction, right? You go from 12 o'clock to 3 o'clock to 6 o'clock to 9 o'clock to 12 o'clock. This is called clockwise, that direction, right? Okay? So we're moving along the unit circle in the clockwise direction, and the picture is saying you're moving along the circle in the clockwise direction. It doesn't matter what the radius is. You're moving along the circle in the clockwise direction, and you have I, J, and K here in that order. I, then J, then K, as you move along the circle in the clockwise direction. Okay? And so this very simple picture can tell you, as long as you're thinking, you apply some logic behind this idea in this picture, you know some things. I can tell you what the other 6 equations here are from this circle oriented clockwise with I, J, and K on it, right? So what this picture is going to say is that I cross J is equal to K. I cross J is equal to K. So if I start I and I move clockwise along the circle, I reach J. I cross J, and then the next thing I get to is K. So I cross J is K. If I start J, I'm starting with J here because these are the I's here, these are the J's here, these are the K's here. So I'm starting at J. The next vector I get to as I walk in the clockwise direction is K. J cross K is equal to I. Okay. Now if I start K here, the next thing I get to is I. And so K cross I is equal to J. Okay? Okay, and so these are the next 3 equations, right? I cross J is K, J cross K is I, and K cross I is J from this picture. Okay. Also, again, these 3 are just from the fact that you take a cross product of vector with itself and you get 0. Okay. The next 3 equations you could remember in one of 2 ways. So one way, if you remember anti-commutativity, you know that if you switch the order of these 2 vectors, instead of I cross J, you take J cross I, you get the negative of what you had before. So if I cross J is K, J cross I is negative K. If J cross K is I, K cross J is negative I. If K cross I is J, I cross K is negative J. Okay? So that's one way to remember these next 3 equations. But to use anti-commutativity, you might use the picture to remember these 3 first. Okay? And so the other way, just using the picture, you don't have to have these 3 equations in order to remember it. For the other, getting it directly from the picture, J cross I, what would happen there is if you started J, but instead of going in the direction clockwise, instead of going in the direction of the hour hand on a clock as time moves forward, instead of going in clockwise direction, you go the opposite direction. You go counter the direction of the clock, counterclockwise. Then, if you start at J, and instead of going this way, you go the opposite direction, the next vector you get to is I. And so J cross I, going counterclockwise, is now you go to Ji, the next vector you get to is K. But now you have to remember that if you're going in the opposite direction of a clock, if you're going counterclockwise, then the resulting vector, you take the negative of it. Okay, and then this circle will help you remember these next 3 equations directly from just the picture without using anti-commutativity, without using those 3 equations and properties of cross product on vectors in 3 space. So J cross I is negative K, opposite counterclockwise. Starting at K here, going counterclockwise, we would reach J next. So K cross J counterclockwise, the next vector, keep going counterclockwise, is I. So K cross J counterclockwise is negative I. And if you start I and you go counterclockwise, the next vector you get to is k on the circle, and so I cross k is the next vector, the negative of the next vector, which is negative j. So I cross k is negative j. Make sense? Okay? And so just this one picture oriented clockwise, you have to orient it clockwise to get the right equations. If you draw the picture right and you remember how to use the picture, you can get these 6 equations very easily. I mean 9 equations very easily, right? The first 3 are just a vector cross product with itself is 0, and then the next 6 you get from this picture. Okay? You have to orient it clockwise. If you orient it counterclockwise, every equation is wrong. And these 6 equations will be wrong because you'll get the negative of what you should get. And so the orientation has to be clockwise in order to remember the 6 equations correctly. If you orient it the opposite direction, again, all 6 equations will be the negative of what it should be. Okay? Okay, so you have to draw the picture correctly. Okay, and so in this note, we now have these 9 equations that talk about the relationships between the standard unit vectors in R3. Those 3 numbers. Okay? Okay, so that's that. And so I'm just going to talk about one more thing about the standard unit vectors on the next board. I'm going to do it with the full board because I was running out of space. Another note, and this is about what I already mentioned in the very beginning of the lesson. I mentioned that u cross v is equal to the determinant of this vector. Right? And I use the vectors I, j, and k here because those are the standard unit vectors from we talked earlier in another lesson about it and in the last board. So u cross v is the determinant of that matrix. Now when you compute the determinant of this matrix, what you get is what you should do is go along the first row and take the cofactor expansion along the first row. Excuse me, sorry. So to define the determinant, use the cofactor expansion along the first row of the matrix, right? Remember, the determinant of a matrix is equal to its cofactor expansion along any row or any column, right? The cofactor expansion along any row or any column of a matrix is exactly the same number. That number is defined as the determinant of that matrix. And so by the definition of the determinant of this matrix is its cofactor expansion along any row or column. And so if you choose the cofactor expansion along the first row of this matrix, you'll get the determinant of that entire matrix. Okay? And so to see why u cross v is why this determinant is u cross v the way I defined it, take the cofactor expansion along the first row, and what you'll get is this. Okay, so take the cofactor expansion along the first row, and you'll get the positive I times this determinant of this submatrix, minus then, right? Because when you take the determinant, you have to consider the signs, right? And so when you move along the first row here, it's going to be plus I, minus j, and plus k, right? And you'll multiply each of those by the corresponding determinant of the submatrix determinant, right? So if you have I here, you get rid of the first row and first column, you have determinant of that. If you're looking at j, you're getting rid of the first row, second column, you're looking at determinant of that. If you're looking at k, you get rid of the first row, third column, and you're looking at determinant of that. And so you're multiplying by I, negative j, and k. I, negative j, and k. And so that sum of products, that's the u cross v. Okay? But I is the vector 1, 0, 0. J is the vector 0, 1, 0. K is the vector 0, 0, 1. Right? That's what I, j, and k are in R3. So if you take this I and you take this I and you multiply it by that matrix, what you get is this vector. Okay, so I'm going to write a little bit extra for you here. And then this is going to be okay, and so if you multiply this by I, you're going to get this in the first component. If you multiply j by that, you're going to get this in the second component. Sorry, we'll put plus and then a negative there. And then plus this in the third component. And then when you add up these vectors, you're going to get this. Okay, so there's benefit to walking through the examples I'm doing at home. And so if you're writing this out at home in your notes, you're taking notes and you're writing all this out on paper, it'll help you remember it more than just watching the video. So I encourage you to follow the steps as I'm doing them and write things down. Okay, so when you add up these three, you get this vector. And so the way what I said earlier in the first board is that u cross v, first board of the lesson, is that u cross v is that. And so this is showing you how you find the determinant of that matrix and how you get this, how you get u cross v from definition. Okay. You find the cofactor expansion of the matrix along the first row. That's how you calculate the determinant that way, and you can get this. You'll get the same answer if you take a different cofactor expansion, but it's easier if you do it this way. Okay, so that's that. Okay. Okay, so let's keep going. Okay, so the next thing we're going to talk about is what's called the right-hand rule. And so this can be a bit difficult to master. Okay, but I'm going to introduce it here. Okay, the goal of the right-hand rule in this context, to start understanding what the right-hand rule means, our goal here on this board is going to be to find that I cross j is equal to k, and that j cross k is equal to I, and that k cross I is equal to j. So we used our picture earlier to write down these equations to remember what they were. And now we're going to use the right-hand rule to see these equations. Okay. So let's say we have the vector. Okay, so the goal is to do that. So I'm sorry, I'm going to give another example where here's u, and here is v, and here's the angle theta between. Okay, fine. All right, so we have u here in this direction, and we have v there in that direction. Okay. And so the right-hand rule is going to describe or show you the direction of the cross product of these two vectors. Okay? It's not going to tell you what u cross v is. It's just going to tell you the direction that it points in. Okay? Right? So in the book, I'm not done with the figure yet, but when we're done with the figure, it will be figure 3.5.3 in the book. I think I just mentioned that now. Okay, so what I'm working on, the picture I'm working on is figure 3.5.3 in the book, if you want to look at it. Okay? So what we're going to do here is find the direction of u cross v. Okay? So in the picture, we're going to find the direction of u cross v. We know u cross v has to be perpendicular to both u and v. Right? I mentioned that in part A and B of our first theorem in this lesson, that when you take the cross product of two vectors, its cross product is orthogonal perpendicular to both the vectors in the cross product. U cross v is orthogonal perpendicular to both u and v. Okay. So now it being orthogonal, we have one of two choices for its direction. Either it's going to go, let's say, in this way, if we draw our picture correctly, or it's going to go that way, right? So the question is the vector going in this direction in the perpendicular direction, or is it going in that direction? Okay? Anytime you have two vectors that are different, they can't, not the same vectors. If you have anytime you have two vectors that are different, not the same, let me put it another way. If you have any two vectors that are not collinear, if you have two vectors that can't lie in the same line, they have this different direction. They can't lie in the same line. If you have two vectors not collinear, in that situation, you could think of the plane that goes through those two vectors. Okay? And so if you want to talk about all the vectors that are orthogonal to both u and v on this plane, that you can put on this plane, you'd be talking about a line perpendicular to that plane. You'd be talking about the vectors that lie on the line perpendicular to a plane. For instance, if you have a regular plane like this, the vectors orthogonal to this piece of paper would be the vectors that lie on the line that's perpendicular to that plane, right? If you thought of a pole going through this piece of paper, you could visualize in your mind how a pole would be perpendicular to the plane, right? Even though it may not make sense, even though you might not be able to reason in your mind, how would I define it as perpendicular? I think you could see in your mind how something, you could call something perpendicular in your mind to this plane, right? And so that pole going through this plane, if you had a vector lying anywhere on that pole, that would be a vector not only perpendicular to the plane, but perpendicular to the two vectors that are on that plane. So if I can put u and v on a plane, because they're not collinear, if those u and v fit on a plane in some direction, right? I put the plane in the direction of the two vectors so that they're on that plane. Then the pole going through that plane is perpendicular not only to every vector in the plane, but perpendicular to the two vectors I put on that plane. Okay, what did I just say? So you have vectors u and v on the plane. And so any vector perpendicular to the entire plane is perpendicular to u and v. So my point is that you only have two directions you can choose when thinking of a vector perpendicular to u and v. Okay? That pole going through the plane, either the vector is going in one direction away from the piece of paper on the pole, or it's going in the opposite direction. Okay? And so the right-hand rule only tells you which of the two directions you have. It doesn't tell you the magnitude of the vector, just which one of these two directions it is. Okay? So what the right-hand rule does is you take your right hand and you first point your fingers, your four fingers, in the direction of the first vector. By first vector, I mean if you're looking at the cross product of two vectors, the vector in the left side of the cross product. So for u cross v, u is the first vector, and v is the second vector. Okay? So right now, if I'm finding the direction of u cross v, here u is the first vector, v is the second vector. Okay? If I was thinking about v cross u, then v would then be the first vector and u would be the second vector in this context. Okay? But okay, so I chose u cross v, so u in this context is the first vector, v is the second vector. I'm going to point my fingers in the direction of the first vector u. Okay? And my thumb is just going to stick out. Okay? Oh wait, let me draw this better. Let's say, okay, I'm going to need to draw the picture so that you can see it on the board, because I'm drawing something three-dimensional on a board. Okay, let's how about if vector u is this way, and v I'm going to put that way. This is the angle theta between them. Okay? Okay, so let's work with this picture. This figure 3.5 by 3. My fingers are going to go in the direction of the first vector u. And my thumb is just going to stick out. Just be wherever it is. I'm not going to relax my thumb. I'm going to keep it pointed like this. Okay, my fingers are pointing towards you, my four fingers. And then I'm just going to curl my four fingers in the natural way, like you're grabbing something. Then the fingers would be pointing, as I curl my fingers would point towards v, the next vector, okay? So what should happen, hopefully, is that as I curl my fingers, they're curling in the direction of V. Okay? If that's the case, then where my thumb is pointed is the direction of U cross V. Okay? And so there's two possibilities. One, either my four fingers are pointed in the direction of U, and when I curl my fingers, they're curling towards V. That's one case. And in that case, wherever my thumb is pointed, as it's pointed outward, my thumb is pointing in the direction of U cross V. So here, U cross V is going out of the board. I'm going to do it that way. U cross V is pointed out of the board. Okay? So the right-hand rule will tell us that in this situation, with U being here and V being there, as I curl my fingers, thumb is pointed out of the board, U cross V is pointed out of the board. Okay? This would be case 1. And I'm saying case 1 is the case that when you point your four fingers in the direction of U and you curl your fingers, they're being curled towards V. Then your thumb is the direction of U cross V. Now, let's say case 2. Let's say we switch the vectors U and V here. So let's say U is now where V was and V is where U was. Right? But I'm still looking for U cross V. I'm not changing the vector I want to find. I want to find U cross V. Okay, so for this example and this example, in both cases I want to find the same vector U cross V. I'm just changing what U and V are. I'm switching them. Okay? By anti-commutativity, because I switched what U and V are, I'm technically finding the V cross U here, right? That U is V and this U was that V, right? So in a way I'm actually switching the order here. And so what I should get is the negative. It should be going in the board. It should be oriented in the opposite direction of that vector. Okay. Now the right-hand rule, without any of that making sense, let's say you take the right-hand rule and I point my four fingers again towards U, right? But now I'm going to curl my fingers, and when I curl my fingers, they're not pointing in the direction of V, right? And so you might say, well, what does it mean pointing in the direction of V or not pointing in the direction of V, right? If I curl my fingers, couldn't eventually I get to V if I just go around, right? Okay. So by pointing towards V, what I mean is that you don't have to go more than 180 degrees in order to get to V. Okay. So if here's U, in order to get to V in this direction, I would have to go I would have to go the really long route towards V. You could say it's more than 180 degrees, or you could say it's the long route, right? The long route to get to V from here would be going all the way around to get to V. The short route would be going the angle theta, right? I'd much rather go the theta way towards V than 360 degrees minus theta, because theta is a small angle, right? I'd rather the faster route would be going in this direction. And so my fingers are not going in the fastest route towards V, okay? This is just a method to remember the direction of U cross V. This is not the logic or proof as to why that's the direction, okay? This is just a memory technique. In no way am I proving to you that that's the direction of U cross V. I'm just teaching you how to remember the direction of U cross V. Okay, so my fingers are going in the direction of U, and if I curl my fingers, I'd be taking the long route to V. And so that means that by the right-hand rule, my thumb is not pointing in the direction of U cross V, right? My fingers have to curl in the direction of V, it being the shortest route to V, right? Here's the shortest route to V. This is not. And so what I have to do now is I have to keep my four fingers in the direction of U, but I now have to flip my hand so that now my four fingers are still pointing towards U, but my thumb is now pointing in the opposite direction. And if I hold my hand that way, then when I curl my fingers now, my fingers are curling towards V in the shortest route, in the shorter route. And my fingers curling this way is going the shortest route to V, and now my thumb is pointing into the board, and by the right-hand rule, that's telling me that U cross V is pointing into the board in that example. So here, U cross V is pointed towards the board. Okay, so U cross V is pointed towards the board in that example, case 2. Okay, so out of the board, into the board, right? To say that my fingers curl in the direction of V, not only does it have to curl in the direction of V, it also has to curl in the shortest route to V, right? That's what I mean by towards V, the shortest route to V. This is the shortest route to V, not that, right? So it wouldn't be this, it would be that. Here, I'm starting at U, right? I'm starting at the first vector there. Not necessarily U, but the first vector. I'm starting at the first vector, and I curl my hands, and this direction would be the long route. I have to flip my hands. Now it's in the shortest route, and my thumb is now pointing in the right direction for U cross V into the board. Okay? Okay, so that's the right-hand rule applied to this U and V. And so, again, I said the goal was to find those 3 cross products. And so we're going to do that here. So in most examples, it would just tell you the direction. But in this special case, because we're cross-producting 2 unit vectors, 2 vectors of length 1, I know that the result has to be of length 1. Okay? So in these 3 examples, I cross J, J cross K, K cross I, I'm cross-producting 2 unit vectors. And so I know the result has to be another unit vector. Okay? And so knowing that the result has to be unit vector, if I know the direction of the cross product and that it's length 1, I know the exact vector. Okay? But that's only for this certain cases. So in this case, I could tell you, using the right-hand rule and the fact that the result is of length 1, I can not only know the direction, I can know the exact vector, right? The vector is determined by length and direction. Okay? Right-hand rule tells you direction, I know the length, and so I can, in this case, I can know the whole vector. Okay, so now let's do that. So the goal, again, is to find that those 3 equations are true. Here's the x-axis, y-axis, z-axis in R3. This is the unit vector in the x-axis, which I'm calling I, the unit vector along the positive direction of the y-axis, which I call j, and the unit vector in the positive direction of the z-axis, which I call k. I'm going to take the cross product of, they meet at the origin here. Okay, so I want to find I cross j. Okay, well, using the right hand rule, my 4 fingers are going to point in the direction of I. They're going to curl towards j. And when I do that, the right hand rule says that my thumb is pointed outwards, which means that I cross j is in the direction of my thumb. And so here I drew z like this. Z is the axis that's coming out of the plane, right? So when my finger is pointing upward, what I mean by that is it's along the z-axis. That make sense? Okay. So if x and y were the board, right? If x and y made up the board, the x-y axis was the Cartesian plane that makes up the board, then, you know, moving out of the board would be like moving in the positive direction of the z-axis. So I cross j is equal to k. I know that the direction of I cross j is out of the board, which is along the positive direction of the z-axis, and it's length 1. And so the unit vector in the positive direction of the z-axis is k. Okay? J cross k. If I start at j, this is where you have to have some ability to like be able to be flexible with your arm a little bit. J cross k, if I have my 4 fingers pointed towards j, right? If I curl my fingers from j to k, they're going to curl in this direction. And if they curl in this direction, my thumb is again pointing out of the board. And what out of the board means here is that the y and z axis were the board. Out of the board would mean the other axis, the third axis, which is the x-axis, in the positive direction. So j cross k is I. Okay? Okay, so going out of the board here means the positive direction of the third axis. Okay, k cross I. Okay, the other one was the hardest one. K cross I, if I start my 4 fingers pointed towards k, the first vector here, and then curl towards I, my thumb points out of the board, And that means I'm moving in the positive direction of the third axis, which is the y-axis. And so j is a unit vector along the y-axis in the positive direction. So k cross I is j. Okay, so I cross j is k, j cross k is I, k cross I is j. And so using the right-hand rule, you can find the direction of these three cross products, and then knowing that each of them are of length 1, knowing the direction and length, I can determine exactly the vectors there. Okay? And so this is a rare instance where the right-hand rule can tell you more than direction. You can also use it to know exactly what the vector is. Okay, so that's an example of the right-hand rule. So actually, figure 3.5.3 in the book, it adds a little bit more than just the vector selection. I'm going to write out exactly what that figure says. So here's U, here's V, and I was using my hands because it's really better to my hands on the board to show it to you than a picture. I'll draw the picture for you now after I explained it. So if you have here, this is U cross V determined by the right hand rule, because here's the picture of my hand. Okay. So I practice this. Let's see if I can draw this hand well here. Okay. Okay, so there's my hand. These are the nails on my hand, my fingernails. There's another fingernail. Okay, so there's my hand. Okay, that's not bad. Okay, so then you curl your hand there, and you're seeing that my 4 fingers are curling from U to V, and my thumb is pointed up. So that's my thumb is the direction of U cross V. Okay. And so that is illustrating the right hand. Figure 3.5.3. Right hand rule. Okay, and here I'm going to write here fingers cupped in direction of rotation. So this is not included in the figure in the book, so I'm adding this here. Fingers cupped in direction of rotation from U to V. Okay, so the fingers are cupped in the direction from U to V, the thumb's pointing in the direction of U cross V. Right hand. Okay, and that area there, that's the right hand. Okay, you may want to pause the video to write down figure 3.5.3. So I recommend you writing it down rather than just looking at it here in the book. Okay, so the next important fact in this section is that the norm, the magnitude of U cross V is equal to the norm of U times norm of V times sine theta. That is equation 6 in 3.5. Okay, that dot is not the dot, it's just the product. That's saying the norm of U times norm of V times cosine, the regular multiplication of real numbers, right? U dot V, when we're doing dot product, that would be an operation on vectors U and V, right? Norm of U times norm of V, this is an operation, this is just a product of 2 real numbers. This is a real number, and that's a real number, okay? So it's not ambiguous when you see a dot here and a dot here as to what operation you're using, right? Oftentimes, again, we simplify our notation, we make less work for ourselves if we use the information around something in order to know what something is. Instead of rewriting information, you can deduce from what you see in front of you. So here, U is a vector and V is a vector. In the context of U and V as vectors, when you have a dot here between them, you're taking the dot product of them, because the dot product is an operation on vectors. If you're taking the norm of vector and dot, and there's a dot here and then there's a norm of v, the norm of vectors are real numbers. And so if you're dotting, if you have a real number dot real number, that's just regular multiplication of real numbers. And so even though you could see a dot in two different places, and they don't tell you the difference on the page, knowing what you're taking dot product of tells you what operation is. So here's a dot product of vectors, here's a product of two real numbers. Okay, so this is a product of two real numbers. We're not dot producting vectors here. Okay, so the norm of u cross v, the length of the vector u cross v, is equal to the normal length of u times the normal length of v times sine theta. And theta is the angle between u and v, okay, in the shortest direction from between u and v, right? So theta is the angle between u and v. And actually, I'll add the word shorter angle between u and v, right? So if here's u and here's v, it doesn't matter which is u and which is v, right? I could even switch them. You don't have to worry about which direction, the orientation or anything, the order. The shorter angle between u and v is just that you have two angles to choose from, right? There's either a larger angle or a smaller one. And so theta is the smaller angle between two vectors, right? If you take the initial point of both vectors at the same point, here the initial point of u is here and the initial point of v is there, you have to make their two initial points coincide. So as long as you start each vector at the same point, then those two vectors will determine two angles, right? One will be the larger angle, one will be the smaller one, and again, theta is the smaller angle, okay? And if the two vectors happen so that they're along the line, and if u and v are just in the opposite direction, and theta, they're both equal to 180 degrees, you can choose either one. The shorter one between them is either one. So theta could be here, or it could be there, because they're equal, okay? So the shorter angle here between two is just the same. So theta could be either one if they're both opposite direction. If they're not opposite direction, then there's going to be a smaller angle and a large angle. Theta is the small one. Okay, so that's the theta in the formula there. Okay. Okay, so theorem 3.5.3. Area of a parallelogram. So area of a parallelogram. Okay, if u and v are vectors in 3 space, so I'm going to write u, v in 3 space, meaning u and v are vectors in 3 space, vectors with 3 components, where each component is a real number, then the norm of u cross v is equal to the area of the parallelogram determined by u and v. Okay, so I find this thing a little annoying. Okay, so theorem 3.5.3. If u and v are vectors in 3 space, then the norm of u cross v is equal to the area of the parallelogram determined by u and v. Okay, so it's easy to understand the theorem. Sometimes it's annoying to calculate. So let me just write down what's happening, what I mean by this theorem. So so again, if u and v are vectors in 3 space, in R3, then the norm of u cross v is equal to the area of the parallelogram determined by u and v. Okay, so let's talk about what the parallelogram determined by u and v is. Okay, so if you have a vector u here, and you have a vector v here, and so keep in mind, we're talking about any two vectors in R3. They could be the same vectors, they could be both 0, but I'm going to use a simple example, and you can extrapolate from that what happens in some weird examples. Okay, so u and v, these two different vectors here, the parallelogram determined by u and v is a parallelogram with adjacent sides vectors u and v. Okay, so if you take the vectors u and v and you place their initial points at the same point, like here, right? That's the initial point of u and v. So if you make their initial points coincide, then the parallelogram determined by u and v is the parallelogram that has adjacent sides in vectors u and v. And so what that means is that it looks something like this. Okay, so there's exactly one parallelogram that has vectors u and v as adjacent sides, right? Adjacent meaning they're next to each other. So here's vector u and v starting at the same point. They're adjacent, and that means that these two have to be their sides. If I chose some parallelogram somewhere else, these would not be adjacent sides of that parallelogram. Okay, so there's exactly one parallelogram determined by u and v, by how we define a parallelogram determined by u and v. Okay, right? So if you find a way to make another one, you're going to have to change what I mean by determined by u and v. Okay, so again, my meaning of determined by u and v determines exactly one parallelogram. Okay, so you have this parallelogram here, determining u and v, and then the norm of u cross v is just the area of that. So the norm of u cross v is equal to the area of that parallelogram. Okay. Norm of u cross v is equals to the area of that parallelogram determined by those vectors u and v. Okay, pretty simple. The theorem. Okay, let's do a calculation. So actually, in addition to the calculation, I'm going to actually also first prove the theorem, or show you why the theorem works. Okay, so if you have u here and you have v here, okay, so I'm going to choose u and v like that, so that way I have room to explain what's going on. Okay, I'm going to make it a little smaller so I can stay on the board. Okay, good. Okay. Theta is the angle between u and v. Right, that's the shortest route between u and v. Okay. What I'm going to do is I'm going to draw the perpendicular from the tip of v onto the vector u. Okay, when we were doing orthogonal components of a vector, we did something like this. Okay, so I'm going to take the tip of u and I'm going to draw a line segment from the tip of u to v to u, to the tip of v to u that's perpendicular to you, like that. Okay, and now I want to think about what's the length of that line segment from the tip of v to u, the shortest route from the tip of v to u. Okay, well, using trigonometry, we know that the length, first off, just given information, that's the length of v, right? The length of that line segment is the magnitude of v. So the length of this side of the hypotenuse of this triangle is the norm of v. Okay, this is theta, right? And so, so if I want to know the length of this side by trigonometry, what I could find was, let's say I call this x. Okay. Then sine of theta is equal to the ratio of the opposite leg over the hypotenuse, the length of the opposite leg, of the length of the opposite side to that angle over the length of the hypotenuse. Okay, so sine theta is the length of the side of the triangle opposite to the angle over the length of the hypotenuse. And what's the length of the opposite side? It's the unknown that we're trying to find. And then the length of the hypotenuse is the norm of v. And so the only thing, what I know is that sine of theta is equal to x over the norm of v. And so solving for x, we get that x is equal to the norm of v sine theta. Okay, so x is equal to norm of v sine theta. And so what we found is this side is equal to the norm of v sine theta. Okay, now if I want to know the area of the parallelogram, most of the work is now done, as long as you see this fact. So here's the area. So I want to find the area of the parallelogram determined by U and V. I want to find the area of that, right? Which I just filled in there. I want to find the area of this parallelogram determined by U and V. So if you take this triangle and you just move it to there, okay? So if you take this triangle and you move it there, right? So you just visualize that in your mind. You just move this triangle from here to here. It's not drawn perfect. I had to stay on the board. You move this from here to here. The length of this is the length of that. That's V. This is the same, and this will be the same. So once you have two sides of the same, this angle, you have ASS. So by triangle similarity laws, right? They're similar, and then you have the side. Okay, so the angles are the same, and two of the sides is the Pythagorean theorem. Okay, anyway, Pythagorean theorem, that'll work. Okay, so this triangle are the same by Pythagorean theorem. Okay, so then if I move this one here, then what you can see is that the area of this rectangle is the same as the area of the parallelogram. And the area of the rectangle is just the length of this side times the length of that side. The length of this side is norm of V sine theta. The length of this side is this part of U, and I just moved the rest of U here, and so the length of this is the same as the length of U. And so the area of the rectangle, so the area of the parallelogram is equal to the area of the rectangle that I'm talking about, right? Area of rectangle means this rectangle. So the area of the original parallelogram is equal to the area of this rectangle, which is equal to length times width. And that's equal to the norm of U. The length of this vector is the same as the length of the one side of that rectangle. So that's the norm of U. Then I'm multiplying it by this side, which is the norm of V sine theta. And so the area of the parallelogram is equal to norm of U times norm of V sine theta. Okay? So the area of the parallelogram is equal to the norm of U times norm of V sine theta. And as a fact, the norm of U cross V is equal to norm of U times norm of V sine theta. Okay? So the area of the parallelogram is this. The norm of U cross V is this equal to the same thing. So this is equal to that, that's equal to that. And so therefore, the area of the parallelogram determined by U and V that's equal to the norm of U cross V. Okay, so actually I'm going to say this is equal to this, the same thing is equal to that. The area of the parallelogram is the norm of U cross V. The area of the parallelogram determined by U and V. I'll write that here. Determined by U cross V. Right? That's the parallelogram, specific parallelogram I'm talking about. Okay, and so this is a proof of the last theorem. Okay, so we just proved theorem 3.5.3. Proof of the one on the last board. Proof of theorem 3.5.3. Okay. Good. Okay, so in example 4, we're going to use that theorem to find the area of a triangle. Okay, so find the area of the triangle determined by P1, 2, 2, 0, P2, negative 1, 0, 2, and then P3, 0, 4, 3. Okay? So I want to find the area of a triangle determined by those 3 points. And so the triangle is just going to be half of a parallelogram. And so when we find the area of a parallelogram using the last theorem, we'll just take half of it, and that'll be the area of this triangle. Okay, so the goal will be to find the area of a parallelogram where this triangle is half the area of that parallelogram. Okay? And again, we'll just half the area of the parallelogram. So the solution is, so here's the x-axis, here's the y-axis, and here's the z-axis. And so P1 is the points 2, 2, 0. P2 is the point here. P2 is the point -1, 0, 2. And P3 is going to be the point P3 is going to be the point 0, 4, 3. Okay, so those are my 3 points there. And so now the triangle determined by those 3 points are just the triangle whose vertices are those 3 points. There's only one triangle with that's vertices those 3 points, P1, P2, and P3. And so the goal will be to find the area of that triangle. Okay, so I'm just going to fill this in here. Okay, so that still says P2, -1, 0, 2. Okay, that's clear. Okay, so that's, P2. That's P2, -1, 0, 2. P1, P2, P3, right there. Okay, so we're going to find the area of that triangle. And so let's just find, let's look at the vector P1, P2. The vector that starts at P1, point P1 and ends at P2, and the vector P1, P3 that starts at P1 and ends at P3. Then the vector P1, P2 and vector P1, P3 are adjacent sides of a parallelogram. And so this parallelogram is the parallelogram determined by P1, P2 and P2, P3. Good. So now that parallelogram that I outlined here, that parallelogram is the parallelogram determined by P1, vector P1, P2 and vector P1, P3. Again, vector P1, P2 starts at P1, ends at P2. Vector P1, P3 starts at P1, ends at P3, in that direction. Okay, and so that's the parallelogram determined by those two vectors. And so if we take the cross product of P1, P2, and P1, P3, we'll get the area of this parallelogram, and you can see that the triangle is half of that area, and so we're just going to take half. So let's put this fact on the board that the area of the triangle